So what I've done is I've pulled a few problems from the quiz. I just want to address a few common issues that pop up whenever doing nomenclature. One thing to keep in mind is that these Roman numerals that you see here, they are only going to be used when you're dealing with transition metals, pretty much. If we look at the periodic table, I'm really talking about, well, I'll just sort of box it in. It's this group, well, right here. It's transition metals, and there's a few others to know. It's really those three that you see most often. You really don't see any of those. If you do see this, it's actually be a +3 because it's in the aluminum family. Tin, lead, bismuth, these tend to vary in charge. Most of the transition metals vary in charge. Like, for example, for iron, you can see a +2 and a +3 charge on iron. And so when we have that kind of situation, then we have to use a Roman numeral in the name to indicate what charge we're looking at. So back in this example, you can see everything is correct except for the charge on the nickel. How do we determine that? Well, one thing to keep in mind is that we can use these numbers on the bottom when they're different from each other. It works every time. Let me just sort of break this down. In this compound, we have the nickel 3 with a sulfide with a -2. And what I want you to notice is that the 2 here corresponds to the 2 on the nickel, okay? And then the 3 here corresponds to this 3 subscript on the sulfide. What this is doing is something like this. It's saying that, okay, I got 2 nickels here. Each have a +3 charge. I have 3 sulfides. Each have a -2 charge. Well, if I add up those values, that's a -6. If I add up these two, that's a +6. And notice what we have. We have equal and opposite charges here. That's what you always see for these ionic compounds. And so when the subscripts here are different numbers, then really you can just use each numerical value to figure out what the actual charge is on the other cation, or other ion, I should say. And so again, since this is a +3, that's why you see the +3 in the Roman numeral in the name. A couple things with this example, titanium phosphide. So one thing to notice is that using the element's name here when you should be using the anine's name. So most of those monoatomic anions have an IDE ending. Actually, they all do. Titanium is in the transition metal group, right? There's titanium. And so that means we're going to need that Roman numeral here. Now notice on this one, this is coming in at a 1-to-1 ratio. Well, again, like I said up top, right? This works if the numbers are, this works. The numbers here indicate the charge of the other ion if the numbers are different. In this kind of example, when it's 1-to-1, well, really what you have to do is you have to break it apart. Now, we already know that titanium, since it's in that transition metal group, it's going to vary in charge. +3, +1, +4, I think it's pretty diverse. The way we know this is a +3 charge is because we know phosphide is a -3. And so that single titanium has to carry a charge that's equal and opposite of that of the anion here. And then once we have that charge figured out, then that's what determines the Roman numeral in there. How do we know this is a -3? Well, it's the periodic trend that shows up for these representative elements here and here. This, if I just count them over, this family always takes on a +1 charge. This family always takes on a +2. This family, yes, +3. Usually it's aluminum is the one that you see. You don't really see these very often. But they'll still take on a +3 if you do see them. The carbon family, they don't form ionic compounds, so they'll be in a separate, they're molecular compounds. And then once you cross over this sort of divide here with a carbon, then you start in the negative range. I should put them up here. -3, -2, -1. And then the inert gases here don't react, at least for ionic compounds for sure. A few of these will form molecular compounds. And there's phosphide, right? It's that -3 charge. And again, we say these are invariant, meaning that they don't vary in charge. Oxygen always forms an oxide ion with a -2. Sulfur, sulfide -2. Selenium, selenide -2. -1, -1, -1, etc. Okay. And again, that's how we know that it's not phosphorus, it's phosphide with a -3. This one is similar to the last example. Gold is a transition metal. So we know we have to have a Roman numeral in there. And again, this is a 1-to-1 ratio between the cation and the anion. We know hydroxide is a -1 charge, and then the gold has to be carrying something that's equal and opposite, +1. All of the polyatomics have a fixed charge. Hydroxide is always -1. Phosphate is always -3. Nitrate is always -1. Now in this example, strontium does not need a Roman numeral. The reason why is because strontium is right there. It's in this family, so it always takes on a +2. So there's no need for a designation of its charge in the name. It's just understood. And that's really the only error in this problem. These Moodle quizzes are designed to ignore capitalization, so it would have, if you had left that out, it would have counted this correct. By the way, you could have also called this bicarbonate. That's not used a lot, but it is used for the carbonate salt here. And then I wanted to pull one of the molecular formulas I was looking at from the quiz. So one thing to note is that you never use the Roman numerals on molecular compounds. Actually, let me back up for a minute. How do I know this is a molecular compound? Well, because what I see, if I find phosphorus and fluoride on the periodic table, and we'll do that in just a minute, they're both nonmetals, meaning, we'll do it in red, right? There's this stair step on a periodic table, and I say nonmetals over here, but pretty much any element on the right-hand side of this divider on the periodic table. So I know some of these are metalloids. They're included in this group that always forms molecular compounds. Now we had phosphorus and fluoride. There's phosphorus, there's fluoride. Now it's a pretty diverse group of compounds that can be formed here. Like the example that I always do is between nitrogen and oxygen. You can have nitrogen monoxide, you can have dinitrogen monoxide, you can have nitrogen dioxide, you can have dinitrogen tetroxide. Okay, so there's a pretty diverse group, and like in the phosphorus and oxygen, they can form a bunch of different compounds. Now, instead of using Roman numerals here, because Roman numerals are dedicated to charges on transition metals, instead we use the Greek prefixes. So a couple things here, right? So di for 2, where's the 2 coming from? It's the subscript there. Tetra for 4, and you can find these prefixes in the textbook for chapter 5 for 092 class. The 4 is coming from the subscript there. And then one other breakdown here. Notice that the first name here, we're just using the element's name. And then on second name, notice we're going to borrow the IDE ending. Now these are not ionic compounds, they are molecular compounds. We'll learn about those when we start doing Lewis structures a month from now. Basically, they're connected together with what's called covalent bonds. So they're not ionic, but we still use the IDE. We sort of borrow this format. The only thing different is that we use these Greek prefixes in front to indicate how many of each that we have there. I think this is a pretty good representative group of problems that I saw on the quiz. So I hope this helped.